Good morning. In the previous lecture, we talked about quantum machine learning, and now we are going to look at how different other components during the quantum machine learning process affects each other. So, if you recall, we talked about quantum computing has three major phases. One is state preparation, one is quantum computing, another is measurement. Measurement is also very noisy, as I talked about. I wanted to show you how you can use machine learning in the quantum measurement process also. So, how is quantum measurement done today? So, basically different qubits when you look at from a quantum circuit, the measurement device will find those values and you are running same experiments many times. So, you are going to use machine learning tool. In the community they are known as a discriminator. I did not come up with that name. So, then discriminator tries to figure out what is most likely based on the probability distribution, what is most likely this value is. So, n classifications or n machine learning is needed. Instead, what we are kind of proposed that because these qubits are coming related to the same circuit. So, if we can use some kind of statistical learning, then one machine learning call would be enough. So, our objective or hypothesis was two things. Machine learning does not give you any guarantee, sure 98-99%, statistical learning gives you guarantees, that is one. Second thing is these qubits, whatever computations they are doing, they are not independent really, they are kind of related. If they are not independent, why are they using separate machine learning to find out what those values are? And it turned out our hypothesis is right. In a classical one, when you in a traditional or existing quantum measurement, you get like blobs of these values. What are these blobs? The different distribution of zeros and ones. Every qubit could be a mix of zeros and ones, and you are trying to figure out is it 0 or is it 1, and then you kind of try to figure that out. What we are saying, instead of treating them individually, try to come up with a function that kind of captures, that is typically known as distribution based classification or cumulative distribution function in statistics. And then two things it happens. So, the existing approaches are expensive, you have to do many of them and low accuracy. This one you will get high accuracy with few measurements. Our objective is to try only once did not work, but that is basically the objective. I want to touch upon quantum error correction just to show you how it is different from classical error correction. So, quantum circuits being noisy or qubits being unreliable, error correction is kind of an absolute necessity. In layman terms, when you want to initialize a qubit to a specific combination of 0 and 1 with specific value of alpha and beta, it is not going to be that way. In fact, quantum error correction is during runtime. So, lot of qubits are working, some of the qubits might be doing fine, some of them may not feel like working that day. So, during runtime the quantum error correction mechanism need to detect which qubits are not doing well or health is not good and provide sufficient reparation for them, so that other qubits do not get hampered and they keep computing. So, that is basically the difficulty, but two major point is in classical you can measure a bit and figure out it is wrong, like error correcting code, and you can fix that, change that. Here measurement is not allowed, measurement collapses the state. You try measuring anybody, it is going to show you 0 value, that is of no use. That does not mean it is actually 0, it might have been correct, you just do not know. Second thing is information cannot be copied, you cannot copy information. That would have been nice, we kind of kept a shadow like the way classical we do, we keep a shadow register, they keep continuing, if branch misprediction happen, we come back, copy back shadow register and continue from there. Copying is not allowed, you are going to get a 0. So, that is why there are a lot of solutions. One of the error correcting code that works popularly is called surface code. It is just coincidentally surface code idea actually came from topological quantum computing. This whole dancing of qubits, how they help each other without getting into the details and theory. Layman terms, if you want to think about, if this is the qubit you want to protect, you put another 4 around it. So, in a classical analogy which is absolutely wrong, when this one loses energy, momentum, these will gain, and they somehow 4 or 5 together maintains the story. So, that is why from a user perspective, if you do not want to deal with error correction, then if you have 100 qubits, assume you have 20 qubits. Every 5 physical qubit would be considered as one reliable logical qubit. But error correction techniques have lot of initial problems, like how do you prepare states. Remember, this is not a classical domain, number 1, and surface code works on the topological world, and you might want to study little bit of topological quantum computing, and you would be amazed if quantum dynamics or qubits amazed you, topology will amaze you even more. It really will seem like magic. Really, such phenomena happen in particles? It does, and mathematicians and physicists know it for generations, but only Microsoft is able to produce it. The final one I want to talk about is quantum verification, and I want to introduce you to a researcher. Remember, earlier in the side channel I introduced, if you want to be a researcher like work like Paul Cocker, publish 5 papers in your whole life, whole world will do it. So, Dr. Urmila Mahadev, she worked in a PhD problem, and problem is interesting. How do you know quantum computer is actually doing quantum computing? It took me 6 months to read her thesis. You might want to read her thesis, you might not want, but the point I want to highlight, if you want to do research, solve a problem, be like her, not like me. Solve one problem, rest of the world would get mesmerized, one problem. And this problem is very important in quantum verification. If quantum computer does not do quantum computing, then all this hula boo is gone, all theoretical guarantees, exponential speed up, everything is gone. There are many, rest of the world is solving tiny corollary problem. If I send a request through IBM cloud and IBM says here is the result, how do you know it actually ran on a quantum computer? Because going through cloud, being in the queue, that takes minutes, hour, if not days, and a classical computer can run it. And anyway, most of the problems you will be solving 4 qubit, 5 qubit problem, even up to 20, 30 qubit problem can be solved using classical computer. Quantum simulation of 20, 30 qubit is possible, 2 to the power 30, 2 to the power 20 is possible. How do you know? But this research problem is much more complex than that. You might want to read and spend 3 to 6 months understanding what she has done. But there are, if you do not want to deal with that problem, if you want to deal with sillier problem, then you want to do in like classical world, if you have 2 sets of circuit, one may be very high level description of the algorithm, one kind of synthesized version it, how do you know they are equivalent? Different transformation you did. If you recall, when I talked about quantum compilation, you start with C like code, Rust code, then you get a quantum circuit, then you get pulses, electrical pulses like your C code, your assembly, then your binary. How do you know this compilation was correct, and you can do equivalence checking and all of formal verification I talked about, people are publishing in those area. Mostly Robert Willi from Technical University of Munich actually published tons of ideas in this space. We worked on also quantum assertions, how do you do monitoring in the quantum circuit itself, and then few other problems we introduced and we felt it is kind of important, which is most people, as I said, when they say quantum computing, they focus on the computing itself, there is nothing wrong. In classical world, that is pretty much it, but in quantum world you have to do state preparation. Remember quantum machine learning, the machine learning tool is initialized in iteration. So, state preparation is important, and then also measurement is important. So, if you create benchmarks where the benchmark is also only measuring your computing efficiency, that is not a great idea. So, therefore, we developed benchmarks that actually takes care of state preparation, computing and measurement itself. And as I said, in quantum error correction, the computing itself has measurement and state preparation and computing also. So, the benchmark should be reflective of all the components of quantum computing. Then the last idea I want to introduce, quantum verification problem. So, remember classical we did the thing, we thought why can't we do this one. First of all, quantum computer is in IBM TJ Watson Research Center, we won't have access to that. Through cloud we use it, and even if we get some result, even if you work in IBM TJ Watson Research Center, I do not think they will allow you to get into that super freezing room and touch the computer or probe into something. You still have to deal it from the outside. You run it, you get the data. So, the way we run through cloud, they probably also run through similar thing internally. So, the question is, if anything goes wrong, what do we do? Almost a decade I spent on how do you debug when things are fabricated, the trace signal selection, all the ideas I developed, a company implements them now. So, I thought quantum domain, let us start something. So, what we kind of see in quantum world, if you say, people will say, oh, those solutions exist, they call it quantum process tomography. For a normal engineer, they said, I have no idea what are you talking about. I ran 2 plus 3, I did not get 5, tell me what to do. You can't tell me, oh yeah, some variation happening, something happening, process tomography we call it, or characterization we call it, does not matter. What we say, we wanted to break it to engineer terms. Let us say this particular is actually the quantum computer, this is actually real quantum computer, and this is actually a simulator, a simulatable model that is parameterizable. We apply a input and we measure, we get some data, and then what we want to make sure, let us say we got a 4 here, actually it should have been 5. Then the question is, what probably went wrong here? Let us say I passed 2 and plus 3, you and I know nobody uses quantum computer to do addition, it is just an illustration. What went wrong inside? It is producing 4 instead of 5. So, the way, if it is classical world, we call it mutation testing. So, let us say inside there is x equal to, if a greater than b, then you do x equal to y plus z or something like that. The mutation testing said, try mutating some of the operator, try changing this greater than to less than, this plus to multiply, maybe one at a time, and see if we can produce 4. If we can produce 4, then we know that is probably what happened. But the problem is, given a program, there would be so many ways you can change to produce 4, you do not know what it is. So, that is what bothered us first. It turned out in quantum computer that probability is low, you will have 1 or 2 solutions that would produce the incorrect result, assuming it is a noise free. If it is noisy, that is another worse problem to start with. So, we mapped it to the machine learning problem, there is a lot of buzzword, just ignore it. Basically, we are trying to figure out, we are trying to modify this model with parameters such that the difference between this output and this output we can minimize. So, this is basically loss minimization problem based on gradient descent, you have remember that from the machine learning, we call it Riemannian gradient descent, and we kind of solve a lot of interesting problems in that. How do you operate on the Riemannian manifold, and how do you know the solutions you get, and solving all that problem is very interesting. And coincidentally, topological quantum computing also works on Riemannian manifold. It just is, everything is a small world actually, but either way then you kind of update this parameter until it produces 4, then it is a loss function, and realizing that the number of solutions possible, changes possible to make it 4 is very small, 1 or 2, then you kind of know that is exactly the problem happened there. So, that is pretty much kind of brings me to the first set of lectures. So, in the next lecture I am going to talk about quantum security. Yes, please.
Sir, we are talking about quantum measurement. So, we are measuring the velocity and the state of qubits, or we are measuring the quantum efficiency?
Those are just analogy, there is no state, no velocity, nothing. It is basically alpha and beta, that is all we are measuring.
Okay.
Alpha 0 plus beta 1, when I say I measured a qubit, all I measured alpha and beta values, or all I am trying to figure out how, what. You remember, you cannot touch a probe and measure it, there are intricate mechanism, I did not get into, I wanted to abstract that out. Alpha and beta for each qubit, that is what we are measuring.
Okay. And the second question is like that, is there any way to measure or observe the quantum system without disturbing it? Because the scene we are measuring the system, it collapses.
Right. So, that is exactly how measurement apparatus is built in. It is kind of a coupling it creates. So, that measurement apparatus is actually classical. It creates a coupling, some form of entanglement, and then so the information get transferred, the measurement equipment is actually not touching the qubit, and it is complicated because if qubit is in the boundary, that you can visualize, okay, there is something, some magnetic resonance, something EM it is going to do, but if qubits are inside in the fabric, it is kind of complicated. That is why you put more and more qubits, the qubit size bigger and bigger, and the chip size is becoming bigger and bigger, because you have to put the probe all the way, all these big wires, big measurement device goes all the way. In fact, that was the hardest problem in topological quantum computer, that how do you kind of, one is how do you create those phenomena that anyons are dancing or distracting each other, either they dance or they kill each other, that is 0 and 1 coincidentally. Question is how do you actually measure it, whether they are dancing or they are in. And so, finding that phenomena, that measurement apparatus, that was the most expensive there. So, this is also expensive phenomena. Yes, yes sir.
What is alpha and beta?
Oh, alpha and beta is, so remember in each qubit, it could be, in each bit in classical computer is 0 or 1, switch on or switch off, but in quantum it could be 0 and 1 at the same time. It is like you are hungry and you are not hungry at this, you are confused state. So, then that is the probability of I want to eat and the probability of I think I am hungry, not hungry, that is basically the alpha and beta, and where the relationship is alpha square plus beta square equal to 1. Okay. All right. So, now we are going to move on to the last phase. Let me begin it fresh.
One more question.
Yes, please.
Sir, when you tell us that quantum computer is answering all the possible ways. So how we know if this is the right answer?
Okay, yeah, that is what Om asked me, that this currently it only works when you know what is the expected value. That is why you keep running and running and doing probability, because right now things are very unreliable. So, you have to know what you are expecting. So, it is the same analogy as in training machine learning. Again, I am not supposed to take analogy. When you are training the machine learning, you kind of know which one is right, which one is wrong. You want to train it to get 100% accurate classification. At that point you can rely on it and use it in the real world. So, what we are talking all this right now is the infancy, because I made my hands dirty, played with this quantum computer. If you are attending any other talk, they will assume quantum computer is completely reliable, you do not have to deal with anything. Whatever you develop, you will get that quantum speed up, whatever quantum supremacy speed up, whatever you are supposed to get. Okay, let us begin the recording, please. Good morning. Welcome to the last lecture. In the last lecture, we are going to talk about quantum security problem, and earlier we talked about quantum machine learning. So, I am basically going to talk about mostly, because the way quantum computer is used today, it used in conjunction with classical and quantum, the machine learning I talked about. So, I am going to look into that, their interactions. Mostly I am going to talk about the key idea of post quantum cryptography, and then if time permits I am going to conclude with some applications of security and interesting trade offs. So, when we talk about classical quantum computing today, you are going to submit your project through or circuit through the cloud, and this is you and I, and this is where actual quantum computers somewhere, depending on which company's quantum computer you are using, it depends whether Rigetti, IBM and Google and Microsoft quantum computers are not available, but there are many other parties online. So, this is basically the classical side, this is quantum side. While your quantum circuit is going through, the same classical attacks are still possible, and while the quantum computer is doing some computing, I will talk about what kind of security problems are happening, and there might be security problems at the intersection of those. So, let us talk about the classical one, and this would be kind of a recap what we did earlier, but I wanted to just highlight only story changes is the information that is, this is more like a cloud security problem, but we are going to look at all of them, and we are interested in the quantum circuit that we are pushing through. That quantum circuit security while it is transit. In the classical domain you might talk about your program, normal data and all that stuff. So, somebody might through side channel do different things, and we talked about power, talked about electromagnetic emanation, we talked about the timing attack, those are still possible to get somebody your the quantum circuit that you are pushing through. And also the different types of integrity violation is possible, whether it is a fault injection, clock fault injection, EM, laser fault injection, different type of integrity violations are also possible when you are sending through the circuit. In the of course, the assumption is attacker has access to some of the cloud computing servers indirectly or indirectly. And then this problem was the favorite one we talked about when we talked about RSA algorithm. If you recall, we talked about one of the key step in the RSA problem one of the key step in the RSA problem, at least in key generation, the idea that you generate an intermediate value of n by multiplying 2 prime number, that can be done fast, but if somebody I give the n, finding this is basically the hard problem. Until around in 1990s, Peter Shor came back and said, here is a quantum algorithm which can do this prime factoring in almost no time, with the assumption the quantum computer is reliable and stable, which is not today. So, whatever it is, that is basically factoring, it is essentially coincidentally, Professor Shao, going back to your thing, it actually uses quantum Fourier transform at the core of the solution. But whatever it is, so that basically started all these flurry of scare, and that started the domain of post quantum cryptography. I will give a glimpse of it very high level, but the key idea of post quantum cryptography, I wanted to just say post quantum cryptography has nothing to do with quantum computing. It is simply the fact, it is still a classical cryptographic algorithm. It so that it was designed or selected in such a way, so that if tomorrow quantum computers are powerful, reliable, they will not be able to break it. That is the only quantum connection, but all of it is classical. The name is post quantum cryptography, it is classical cryptography in the post quantum era. Even if there are quantum computers, it will not be able to break it. In layman terms, in RSA, it is basically you are dealing with prime numbers or prime multiplication. Then people thought those are weak, they moved to elliptic curve to make it even. These are taking normal integers, elliptic curve takes only the points on the elliptic curve, additional level of complexity, and in the post quantum cryptography is really it is a lattice based cryptography. So, it is I will not say exponentially, but significantly more complex than the previous one, right. So, now I just want to give you a timeline idea what actually happened in, although Peter Shor did it in 1990s, people take lot of time to digest it, government took lot of time to adjust and get billions of dollars, different countries, and actual competition started into the initial call was in 2016. So, there are 69 submissions, 69 possible cryptographic algorithms, and 2019 from 69 NIST selected actually 26 of them, and then finally 2020 there are 7 third finalists with 8 alternates, and finally 2022 about 4 was accepted, and most people do research on these two, crystal Kyber and crystals dilithium, these two most people do. So, there are I believe 2 encryption and 2 digital signatures, there are 4 of them, but whatever it is, this is basically the standard today in most of the world. When they talk about our security algorithms are post quantum resistant, they basically use these algorithms. And as I said, even the day it was announced 2022, just few months before, some folks published that even these algorithms can be broken by side channel attack. So, of course, it was not designed for side channel resilient, in fact, it did not even have side channel mitigation in them. Once you put mitigation, maybe it will work, but nonetheless they are side channel resilient. And kind of just to instead of showing what those algorithms does, I wanted to show you why the side channel community was so successful, because the day it all started 2016, people started attacking all the stuff, and the people who were able to demonstrate here, they were already breaking things, and I just want to give a glimpse of that. Oh, before I do that, so all these kind of security algorithm, if you kind of see for different kind of categories, this is digital sign and authentication, public key encryption. So, different algorithms are in different categories, when initially all of those are there, and then some of them got selected. But what I want to show you, this side channel attacks, oh, of course, this we already know how this attack happens, but in the crystal Kyber, one of the ones that I said there are 2, dilithium and Kyber, and crystal Kyber, if you look at the attack, they are basically doing effective message recovery attack by deep learning based power era. Remember, these are classical cryptographic algorithm. So, all the classical side channel attack works on them. This is like normal algorithms, right. So, then message recovery attack happened, and then there are many variations, sliced multi-bit error injection technique, effective message recovery, valid ciphertext, recovering the session key, and then people are doing attack on multiplication algorithm. All of that, the previous slide I said, they based on different type of multiplication algorithm, and people kind of figure out how to break those multiplication algorithms. So, people are not trying to break the theoretical guarantee of the algorithm. People are trying to break the components it used to build the theoretical guarantees. Can I break some of the components? In fact, if you remember elliptic curve cryptography, before Montgomery multiplier was introduced, the original multiplier people just broke the, I think the almost at same day or within a month of elliptic curve cryptography was introduced or accepted as a standard, somebody broke it by breaking the multiplier, and that then they changed it to Montgomery multiplier, and that happens to be resistance to those type of attack. Here the first thing they went for multiplication algorithm, and then there are also different variation point wise multiplication as threshold level, secret parameters in the scalar multiplications, and different parameters they are able to break. So, then CPA, what is it? Correlation power analysis. So, that attack retrieve the secret key, and there are variations, divide and conquer strategy instead of doing brute force, and then again from the multiplication and entity coefficients with only 200 traces. So, side channel community, one of the interesting factor is how quickly can you do it. Even in obfuscation, when Professor Karfa talked about it, when you say something is really strong, then you say how long the SAT attack will take to break it. If it is long enough, then you call it okay, reasonably secure, right. Same thing for side channel attack. If you need millions or billions of traces, of course, then you have to say how long does it take for me to get that traces and analyze it. If it is months and years, then people will say, well, that is reliable enough. So, 200 traces basically I can do it in no time. Then attack on message encoding functions, there are many variations. I am not going to go through laundry list, except to say if you want to start in this domain, you are already behind by at least a decade on the side channel attack on cryptographic algorithms. People started in early 2010 almost, right. So, that is about on Kyber, and you should not be surprised, same thing for dilithium. Let us see how I started here. Oh, the animation goes in a wrong way. So, basically all of those, so in PQC algorithms, Kyber, Saber, NTRU, and many of these algorithms, electromagnetic side channel attack actually works reasonably well, and they are able to say secret key extraction. And then somebody came up with a masked implementation of Saber algorithm, and people are able to do deep learning based power analysis and able to successfully get the key. Then this NTRU, that multiplier leakage of, so basically leakage of the target processor, private key recovery, single trace. Oh, this is actually one of the interesting work. One trace will be able to break the key just using one trace. So, that is actually interesting idea. So, there are a lot of work happened in post quantum cryptography space, but most of the attack, I do not know, I have not seen any attack where people actually broke it mathematically or the logic or any flaw. I did not see that, but all the break are on the side channel space. So, there are a lot of countermeasures, people looked at it, and those countermeasures happens to be that you have already studied or looked at. So, masking is one of them, but it is not quite effective, as you can tell, and then there are some solution. So, basically people are then trying to do, can I do some kind of test vector leakage assessment. Remember we talked about leakage assessment of this implementation, and then find the vulnerable modules, and then kind of try to reduce their leakage, information leakage and all that. So, there are a lot of effort. This area is kind of new, 2 to 3 years old or 4 years old. This might be a good area to get in. So, now that I am done with post quantum cryptography, I am going to move on to quantum devices itself. What are the security problems do we have? And so, the most of the problem on exact this space is by Professor Yakub Shafer. So, he was in Yale University, I believe he moved to Northwestern or Northeastern, but most of his work by Yakub Shafer, and you want to look at that. But I want to just highlight 1 or 2 problems that people looked at. And in the post quantum, in the quantum security, people look at the security of the microwave generator, as well as, let me skip this, you already know. People also look at the quantum computer itself, what is going on in the quantum computer. Remember, we do not have physical access to the quantum computer. So, somebody trying to attack has to do something like the attack we talked about, like cache timing attack. Somebody brings something there. So, the analogy here is when a victim kind of computes something and then there is idle period, and then IBM, let us say it is IBM quantum computer, IBM does internal reset, and then the attacker wants to map the quantum circuit to the same qubits. Reset does not work completely. They are able to recover what was the computation done by the victim. So, it was actually at that time that was actually a problem, that the reset was not big enough, not long enough to put it to the 0 state. Some residue was there, whatever alpha beta residue. Now, I know this sounds silly, the things are so unreliable anyway. For normal mode, somebody stayed idle, somebody did reset, still you have enough information to break it. It does sound silly, but then again let us not do rational discussion with quantum computer. These researchers are able to figure it out. So, that is basically state retention problem. And then, so these researchers have published lot more. I just wanted to explain two of them that conceptually can be explained. The second one is, let us say you have enough qubits in the machine, something like this. Let us say you have enough qubits in the machine, and let us say your quantum circuit you map to the, recall how do we work? Qubits are more like FPGA lookup table, you program them, you send pulse, you say these from now on these two guys are married, that is entanglement. These two guys should not talk to each other, that is kind of whatever, you put a gate and you block, you make them talk, you form gate basically, and all you do by sending pulses. Those qubits are physically sitting in the same place. You can do swap gate and there are all these complexities, but let us say one of the program is running on this. Normally that is not how it works, normally it works mostly this way. Let us say you have 4 qubit, one quantum circuit is running on these two, another running on these two. So, the top one could be the victim's quantum circuit running, the bottom one could be attacker circuit running. Then there could be a crosstalk like behavior. So, this qubit might be able to figure out what is in this qubit. Of course, ideally this attacker, if this is the attacker would try to do an entanglement with that, but the design itself might prohibit it. So, basically whatever kind of influence you get, that is the crosstalk, and the crosstalk is also a known phenomena in classical domain, and the phenomena is something like you are sending a 1 here and here is a line 0 here. This could be a bus between processor and memory. The crosstalk thing, if these lines are very thin, they are very close. So, if this line is 1, this line is 0, think of a capacitance, this will kind of, this capacitance is supposed to be empty, but this capacitance will charge, and this might be more than 0. If it crosses above the threshold, suddenly this 0 will become 1. Converse is also possible, if this 1 is a weak one, capacitance is just barely above the threshold, this 0 will try to pull it down, and if it just goes below the threshold wherever it is measured, then 1 will become 0. So, crosstalk is not a new idea, in fact crosstalk problems in nanometer regime is actually more, and anybody who does layout or below, they will talk about it, that is all they do all their life, parasitic and crosstalk. So, crosstalk kind of behavior the researchers utilized to kind of figure out what is the information that victim is computing. And again there are mitigation techniques. There are a lot of mitigation technique like insecure reset, and this I talked about. There are techniques that how many times you need to reset, or the reset operation. Think of reset, remember those qubits does not know anything, you send electrical pulses, they get oriented in a certain way, right. You give a chocolate to a kid, they behave differently, but once the chocolate is over, the kid starts behaving exactly the same way. So, therefore, the reset, maybe how many times you have to reset and all that, there are mitigation techniques people talked about, that reset that guarantees that the state is actually gone, and so there are also work on how do you mitigate this problem. There are other ways of mitigating. If you recall, we introduced the idea of quantum steering. How do you use quantum steering to kind of mitigate some of these insecure reset? And this one we talked about crosstalk, and crosstalk all kind of behavior you can kind of mitigate through good compilation technique. you can do good compilation technique. I did not get enough time to talk about many of the classical compilation optimization problems still applies here, because even classical compilation you are trying to make area small, power small, performance faster and all that is the same thing. But here in addition we have one more parameter, reliability. Do I have to run these electrical pulses once, can I get the result, or I have to run it 10 times? How do I run minimum number of times and still get accurate, the fidelity of the things, that is the compiler's objective. So, now that we have little bit of time, I am going to talk about, before I conclude, the application specific security. All the security problems and primitives we talked about in classical and quantum domain is applicable to any domain. But when you look at in a specific domain, the security problems or applications or solutions are different. So, I can talk about many domains, but I am going to talk about one or two depending on the time. So, I want to start with the car, right. So, throwing a car out of the road without you being there is kind of trivial. Anybody knows why? Anybody's car can be thrown into ditch, whether you violate a law out of it, I do not know. Anybody knows why this is possible? I can sit here, you are driving, crossing the bridge in the Brahmaputra, I can take your car turn any way I want. Why is it so easy? Anybody can do it, even Om can do it. How is it possible? Because there is an inherent story to this car. A car basically lives, or the car design lives somewhere around 30 to 40 years. You may not feel that way, let me elaborate. When a car gets designed, or the blueprint, or the whatever the paper, when you design, you have the design in the paper, and when it is on the road it is 30 to 40 years. I am not talking about the exotic cars people maintain and vintage cars, I am not talking about regular cars. Because the thing is, when it is in the paper, depending on which country it is designed, they have their laws, they have to get it approved. That would take you somewhere around 2 to 5 years to get approved, whether there is a seat belt law or whatever law it is. Then once you have that, you design and dealer and sell, that you are looking at 1 to 2 years time span. When you buy, most people even in the rich countries, they drive 5 to 10 years, and then that car does not go to the dustbin, somebody else buy, continues. So, think about a security mechanism that was built 20, 30, 40 years ago. Even a baby who is not born can break it. So, the part that is even worse in automotive system, automotive standard does not allow any security verification and checking, which I will explain in a moment. So, couple of things happened. One, I am saying security built in 20, 30 years ago is not going to work, and it actually should not be a surprise. 20, 30 years ago nobody used to talk about security. So, all the buses, the bus protocol where all the components, embedded devices are connected, they have no built in security mechanism, none at all, right. So, if you recall, we talked about reconfigurable security. If it was implemented in that, you can take it to a dealer, and if you want to pay, they might upgrade, but it is not even designed that way, right. There are a lot of bus configurations over the years that were built, and now these days whatever bus configuration they are developing, they have security in mind. But in same analogy applies 20, 30 years later, if it is not upgradable, modifiable, it would look like a joke, anybody can break it. So, that is why when I come to India, I go home always with this one. This may break, doors may fall, it has no electronics, and production stopped sometime in 2014, but it still works. In Kharagpur you still have in abundance of those. And but any other car, depending on when you bought and how much money you paid, it has tons of electronics, doing tons of sensing, actuation. Remember when I talked about firmware security, it has lot of electronics and lot of vulnerabilities, lot of points of attack. And in fact, most of the attack in the first page I showed, they try to attack the infotainment system, even the advanced car infotainment system, where you have all these. Early days you used to have CD player, these days I do not know what you have, those are not secure. So, people get access to the infotainment system, then they get access to the engine control system, and then they make the attack. To make matters worse, all these so called smart cars like smartphones are really unsmart. They have machine learning in it. This is the first time I am talking negative about machine learning. So, because you have the machine learning in there, machine learning model, and they are trained, and then anything happening, wrong decision is making, information is flying to the cloud. At the end of the day, when you are doing charger or it's resting, the machine learning model from the cloud is basically updating to the new machine learning model. Maybe the observation of your car, maybe many other cars reported, the machine learning in the cloud got retrained based on that, and it comes a model. So, vulnerability here, vulnerability in communication, vulnerability in cloud, tons of vulnerability you are carrying with. If that is not enough, then machine learning, the autonomous car or community has no notion of security verification. They have something called ISO 26262. Safety verification. So, even if you are driving a car and suddenly you feel the sky is going to fall on top of you, the car, autonomous cars, when you do not have a control, they are not going to stop. They will do something called graceful stopping. The car will, in your computer something looks wrong, ransomware, you press the power button and stop it. You cannot stop in the middle of the street because it is a danger for the passenger. So, that is why safety verification problem is passenger's life is more important than China trying to hack a computer or Pakistan trying to hack a computer from your car. Nobody cares. So, passenger's life or safety is paramount. That is basically the functional safety, and that is the verification, that is the guarantee everybody worried about. So, in this domain everybody has a different focus altogether. Now, that is why I have this long life for automobiles actually makes it so easy, even a caveman and cavewoman can break it. Ohm can break it faster than them. Now, it is time to conclude. I want to show you two perspectives from different people, but before I show that I want to kind of recap that we started with the story today's security is not enough and what are the vulnerability. We kind of looked at the landscape of vulnerability. I kind of talked about if you want to start research, start here. So, where you have all the vulnerabilities and attacks known as of today, and as it should not be surprising, then we kind of know everything. What are the attack goal, what attacks are possible, what are the countermeasures, and it is a cat and mouse game, whether in hardware, firmware, software. Attacker also know you have this mitigation, they will come up with better attack, better kind of attacks, and you try to mitigate. So, it is kind of going to go forever in every domain. If that problem is not enough, if you kind of put other conflicting requirements, I want to pull in just two examples. One is security and debug. Security should be clear, we talked about security for 10 days. We are trying to stop, pause the vulnerability. Debug problem is, think of the engineers in the company, test and verification engineer, their objective is to just to verify the design. So, what does debugger want? Debugger want the full visibility of everything, software, hardware, firmware. If I can do printf of every variable, that would be ideal. But the security engineer says no, 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 do not come close to the variable named key, do not even come 1 million radius from key, not even this variable x, because if you know x, you will be able to infer y. Security community does not want to have any visibility, zero visibility. Verification community want full visibility. This is a constant fight in every company. Anybody knows how this fight is resolved? Because security people cannot win, because if you do not let me touch anything, how on the earth am I supposed to verify your security module? Forget about my functionality of the rest of the design. How do I verify your security module will encrypt correctly, key will travel correctly? How would I verify all of that? The way it resolved is that, remember, debugging we still have trace buffer and all that post silicon, we still have those notion of the tracing or trace buffer. It is just that trace buffer is not allowed to have any variable which are security or sensitive variable, not even variable that through contact tracing or observability tracing you can observe. Now, that still does not solve the problem how the security engineer will, the verification engineer will verify. During design time, it has full visibility or some form of visibility. When you sell it, you kind of lock and block it. That is why when you have a design, you send it to your company, and sometimes your friend get a refurbished version of it, you get a new version of it, that is the catch. If the problem is in the security area, they triage and find it, they will not be able to debug any further. So, they give you a new device. But if the problem is in the other area, they will just fix it, do firmware patching, do something, and then give your own phone back when they can fix it. But whatever it is, this conflict is not going to go away anytime soon. So, security problems are going to remain relevant. One last thing I want to talk about, security and reliability conflict. So, I worked extensively on the pacemaker, neurostimulator and all those for a long time, and I got interested. I went to go to a neurosurgeon, and they were digging literally holes on the top of a brain, and I am like curious, what are you doing? It is like, it reminded me, this oil exploration. They dig hole here, dig hole there to see if you have petrol, diesel, whatever, I do not know what they extract. So, they try to find where, which one?
They extract petroleum.
Petroleum. They extract petroleum wherever it is. It is as if the brain, and I am like, I literally asked the neurosurgeon, his brain would be damaged. He said, oh, these guys' brains are damaged. So, I am talking about countries where people live 80, 90, 100 and more, and many of them has dementia, whatever, Alzheimer and all kind of diseases. So, the objective is you put a stimulator, and then it will generate pulses in the range of hertz, not megahertz, not gigahertz, brain operates in the hertz level. So, in the hertz, and if you do in right place in thalassemia, right place in the brain, then you might be able to move your right hand, left hand and all that stuff. And now, the same thing in the pacemaker. Pacemaker, basically there is one nerve that basically comes in an ventricle. So, it tells the ventricle to pump, so that blood goes to the thing, and if that pulse does not come, it does not pump. So, that is why it artificially generates that pulse every, I do not remember, 16 millisecond or whatever, it generates that pulse. It monitors, did the pulse arrive? If it does not arrive, then it generates a pulse. So, all of this is perfect, but the problem is the attacks, basically Kevin Fu's group basically showed that you could have a $20 kind of apparatus and make anybody die, and you will not go to jail. How does that work? Because these devices have transmitters, and when you send the signal, it becomes on, starts receiving, otherwise transmitter stays down. And why that mechanism was there? Because in early days, before 1990s, anytime you want to put a pacemaker or you want to put any of those, you have to do operation again, take it out and replace it. If battery is not working, something went wrong, people thought, why do you want to do that? Most of the time things are fine, some settings need to be changed. So, that wirelessly doctor can change the settings, that is when those stuffs are in. And now, anytime you put a technology, people did not realize what will happen, and then some researcher came up with the idea, I can turn on and turn off the transmitter million time in few seconds, your battery is down and you are dead. At that time there was no law, this is not a secondary murder, not a second degree murder, but anyway, whatever that is, and that time US Vice President basically Dick Cheney took out the because of that, got freaked, everybody got freaked out. It is like post quantum cryptography. When you hear this, oh, I am sitting there, somebody playing something video game and I am dead, they just took I would rather die from arrhythmia than just somebody making an attack. But anyway, all this story I do not want to go further detail. What I want to talk about, question is, why did not they put encryption in it? Why anybody with any signal can communicate? It should be only the device given to the customer or the patient or the doctor, and that should have all the authentication, encryption we talked about. Any thoughts why it did not have any of those?
The same card technology is happened here.
No, encryption authentication is known for a long time. These stuffs and these are all in hardware for a long time. So, building this into this device is not a problem.
Sir, could you please repeat the question once more?
Why authentication encryption was not built in? Anybody can buy any device, keep sending signal, ideally it should not accept those signal, right? Yes, please.
Sir, cost and second is resource use. If we are going to implement encryption in those sensitive device, it will have resource impact also, and cost will be increased twice or thrice.
Right. So, you are on the right line. If you, because I am going to say something you won't believe. The people who get most paid in any country is heart surgeon and neurosurgeon, and they are the most idiots. So, when I started talking, this guy is referring this thing as a battery. I am like, on earth, why are you calling it battery? Then I started talking to so many people, every doctor refers to this as a battery, because 98% of it is battery. But for people in computer science or electronics or electrical, we see it as electronics. It did not occur until then that electronics is less than 1 or 2% of the story here. For everybody else, it is a battery. They did not even thought it is needed to be controlled, preserved. There is no stuff. Even doctors do not know. I asked them these companies like Medtronics do not sell these devices. Only doctors and hospitals can buy them. So, then how do I do research? I asked this guy and he gave me a bag full of things with blood in it. I said, what am I going to do with this? Oh, there is enough battery life left, 1 or 2 years you can do research. Then my dean said, you can't use it, your lab is not biologically certified. Then the medical people also pushed back, the doctor is not supposed to give that to me because this has personally identifiable information. That is when he started saying this is a battery, and then it occurred to me. Anyway, so the thing is, we always see things from our side. You have to look at people from other side, the people who are designing, the people who are using, they think it is a battery, and because it is a battery, so then battery life is the primary objective for everybody. Putting encryption will cost around 30%. So, typical battery like this lasts about 8 to 10 years. Now, if you put an encryption, it would reduce by 3. So, if I put it on myself, every 7 years I have to change it versus every 10 years. So, that is basically the deal, that is one, but that is not the reason why people did not put in. What do you think else is the reason? The reason is, if it has an encryption, it has a key. Who knows the key? It is only me. If I go to a country, choose your country, the least favorite of yours, Pakistan, right. So, if I go to Pakistan, something happens to me, of course, first thing you will say, why the hell you going to Pakistan in the first place, and the doctor gets to me, I can't talk, and by the time they try to connect a consulate and go to the country, home country and find the key, I am dead. So, my reliability problem or the security problems, my reliability problem. So, there are many such things we do not think about, and we just pass comment, oh, they should have just did this or that. Now, these days some variation of encryption is actually in place, there are some mechanism, that is why the medical thing, this approval process takes so long. There are different checks and balances, but nonetheless I wanted to just give you idea that security, whatever you learned, when you try to apply in different domain, you have to understand that domain's sentiment. You do not want to hurt anybody's emotions. With that, I basically want to conclude. So, basically in this whole course, we talked about there are wide variety of security vulnerabilities, and we kind of talked about AI or explainable AI is very promising, and I hope you actually learned and you will use it for your work. Thank you.
So, let us give a big round of applause to Kaushal Mishra. So, his energy level always inspired me at least, and I hope it inspired you as well. He is 53, but he always behave like a 23, right? He's always, you ask him to go to my lab, ask to discuss some research, he will always agree, right? So, he's a very, very energetic person, and if you are working in this domain in future, and if you are getting trouble, feel free to contact sir, and I'm sure he will help you in technically and in other way also.